Okay, good evening, class. So, last week said we discussed about redox reactions, oxidation reduction reactions, and there we talked about the definitions and how redox reactions take place. We also talked about oxidation number. So today we are going to finish up our redox reaction. So we see how to balance ionic reactions, how to balance redox reactions, and then test for oxidizing and diffusing agents. Now, for complete redox reactions to take place, there has to be two parts, and these two parts are mostly ions. So, we will see how to balance these ionic reactions, and there are two types of these reactions or equations. We have the simple half and the complex half equations. So for the simple half equations, they contain simple ions, which are usually products of oxidation and reduction of the half that is provided. So it's either the oxidation half to balance or the reduction half to balance. For these simple ones, we have just three steps that have to be followed. The first step is that you have to assign a oxidation number to each atom of the element in the application. Remember, we did some rules last week for assigning oxidation numbers. That it is a neutral atom, that an element is neutral state, the oxidation number will be zero. If it's an ion, the oxidation number will be the charge on the ion, and we can still determine the oxidation number based on the atomic number of the elements. So those are just all the rules and assigning oxidation number. The second thing we do after assigning the oxidation number to balance the number. You see how this is actually carried out. And after balancing the number of atoms on both sides, we now make sure that these um, atoms have the same number on the product and reactants. Why is this so? Remember the law of conservation of mass, that matter can neither be created nor destroyed or can be converted from one form to the other. So for this reason, we cannot lose the number of the atoms. It has to be the same on the reactant side and on the product side. So you have to make sure these numbers balance. But when we are trying to balance these um, numbers on the atoms, we can only add coefficients, but we cannot touch the subscript. We can only add coefficients, but cannot touch the subscript. So you see what this actually means. Now, after you've done this, the third part will be to add the appropriate numbers of electrons to account for the change in the electron number. So on the product side, there is addition, and for the reactant side, you have to, or that is also have to add, but if we see how it goes. Let's just use this example first. For this one, we have ion 3, then converted to ion 2. Now, this first part is the one half of the equation, just a simple equation, ion 3 to ion 2. Now, assigning the equation number, we use the number of the charge on it, here being plus 3 ion 3 and plus 2. Just that the number on it is the oxidation number. Now, the change of the position number of ion from 3 to 2 means that there is a decrease on the reactant side to the product. Now, to account for this decrease, we now move to the next stage, which is to add to the electron number. Notice we missed a step, which is adding to the number of atoms. Why we are not adding to the number of atoms is because we have one atom of iron on the reactant side and one atom of iron on the product side. So there's no need to add number again. If you have add again, it means we have to add to both sides, but it's just a ratio of 1 to 1. So there's no need to add any number. So adding the electron to it, we add one electron to the left side. Why? We are trying to see, okay, remember, electrons are negatively charged. So what I try to see is what number in the negative will do the adding to make sure both sides are balanced. If we have to add electrons to the right side, which is the product side where the Fe2 is, it will reduce the Fe2. But now adding it to the reactant side, where we have Fe3, there would reduce Fe3. So if we just use our calculators and do plus 3 plus minus 1, that would say plus 3 minus 1, that would give us minus, that would give us plus 2, sorry. So for that reason, having plus 2 there, it will make the left side to balance with the right side. So that is how to balance simple reactions. Get the observation number. After I get the observation number, if there is a need to change the atomic or the number of atoms, I just because there's no need to skip that and move to the next stage, which would be to add to the electron. Remember once again, the electron is negatively charged, so it carries a minus sign. So whichever side you're adding it to, you will know that that side will be reducing. So that's what happens here. So we have Fe3 plus E minus, which stands as 1A minus, will still give us Fe2 plus. So that's for that. Now, this is another example here. We have I. So originally, what we have is um, originally what we have is I to give us I minus plus I minus. Now, the thing here is, first of all, we have to do what assign position number. So once I assign the position number, we have to make sure both sides are balanced. Now, we have two atoms of iodine here on the left and one here. So to balance this, remember, adding to the coefficient, we have 2. So that's why we have I2 and then 2I minus. Now, by doing this, what we now have is I2 minus 2 is 0. Why is this? Iodine here is diatomic, 2 tons of iodine. And remember, it means original state. Okay. So, because it is original state, so normal state as an element, free state, so it carries 0. But on the other side, we have 2I minus. Now, what that means is the position of I to 0 and the other side is going. So for us to now balance this, what we now do is add 2 electrons to this side. You can see that we are done here. Adding 2 electrons to this side, having minus 2, and now minus 2 plus 0 is still minus 2. And that is why we have this side in minus 2. We don't have minus 2. With that, we have balanced the reaction. So that's how we go about it. That's what we're doing here. We added the atomic number to balance the elements on both sides. Then after that, we now check the position number and balance the charges there with electron. It's that simple. Just remember every time that the electron gives a negative number, so there's a reduction. And that's very important. So that is for the simple one. And what about complex reactions? For balancing complex reactions, these complex reactions are those that involve oxygen, that is ions that have oxygen attached to it. And because of this oxygen attached to it, there might be addition of water molecules or hydrogen ion or hydroxide ion, depending on what is required in balancing. And this is what makes it effective. And for this reason, we have about six steps. First step is we have to balance all the atoms, set those of hydrogen and oxygen. Then we assign oxidation number to the atoms that are changed. We add the appropriate numbers of electrons to balance both sides, for the electron gain and electron loss. We add the appropriate number of water molecule to balance oxygen atom. So the water molecule balances oxygen atom, while we add H plus to balance hydrogen atoms. We'll see how this actually goes. So we can now check the chart. Now this is an example of what we're talking about here. Here we have that of manganese tetraoxide or tetraoxide 7, sorry. So when you break down iodine, it gives manganese 2 plus ion. And for that to have occurred, that means there has to be a loss of hydrogen. When hydrogen and sorry, oxygen has been removed for it to now be attached to free hydrogen in the form of water. So first of all, we balance the atoms on manganese. And balancing atoms on manganese, you know, because we have one atom of manganese on the left and one atom of manganese on the right. So since that's the truth, next we need to assign oxidation number. Oxidation number of manganese of tetraoxide is plus 7. If we go back to using our um, formula we used last week on calculated oxidation number, you get it as plus 7. Meaning that what you have, let's say we do not know the oxidation number of manganese, but we know that of oxygen to be minus 2. So we have only one atom of manganese there. That 1 times x, close the bracket, plus on the other side minus 2 times 4. Plus we have minus 2 for the oxygen and then 4 as the number of atoms of oxygen. The time you interpret, you have plus 7. So we have plus 7 for manganese and then plus 2 for manganese area. Now, balance the number of electrons here. We now check, okay, how many electrons do I have to which side to make them equal? Remember, electrons are negatively charged. So checking that out, that will, you see that on the left hand side we have plus 7, the right hand side we have plus 5, plus 2. If we add anything to the left hand side, or the right hand side, it will reduce it to say 1, 0, and 5. So if we are adding electrons here, the other side, so we have the test of the manganese. There it will be given to plus 6, plus 5, and the rest. So what number do we add? Obviously, that will be minus 5, because plus 7 plus minus 5 will give us plus 2. So that means the number of electrons we'll be adding will be plus 5. So that's what we have here now. So that will be NNO4 minus plus 5 each on the other side. So what will that leave us with? So we have NNO4 minus plus 5 each. Remember that we have oxygen here, and we need to balance both sides. As we said, conservation of mass. So to conserve the mass, we add water to the right hand side. Adding water to the right hand side, we have to add 4 molecules of water. Because in 4 molecules of water, we have 4 atoms of, 8 atoms of hydrogen and 4 atoms of oxygen. That balances the oxygen. After balancing the oxygen, we have to also balance the hydrogen. Once we do that, we now add 8 ions of hydrogen. Adding that out, I can solve everything. I can check. On the final equation, we have manganese on the left, 1, manganese on the right, 1. Oxygen, how many do we have? We have 4 here. On the other side, too. Checking it out, we have 4. Then Hydrogen, hydrogen here, we have 8. Hydrogen here, 4 times 2 is also what? 8. So at the charges balance, going down here, we check the charges and ensure that we have balanced charges on both sides. Now that's the complicated one. So we follow the whole 6 steps. First of all, starting from here, balancing the number of atoms. Since there are no atoms to balance, so we leave it like that. We come down here, assign the station number plus 7 and plus 2. Then we use that to now check how many electrons do we add. Because electrons are negatively charged, we have to check which side do we add negative charge to. That when it reduces, it will be the same with the other side. So that's why I added minus 5 here, so that the minus 5 electrons there. Minus 5 plus 7 will give us plus 2. We have to then have the ion electron method or the exhibition number method. So the same helps use both methods now. So the ion electron method involves splitting the redox equation into oxidation and reduction halves, and then we have the reactant and the product of each reaction, which are usually provided. And there are 6 steps after you have splitted the box. Now, what are these 6 steps? First of all, you assign the oxidation number, which is steady. Next, you now separate the equation into expression and the reduction half. So you balance each half before you treat them as either acid, neutral, or alkaline. For acid, that means the hydrogen has been reduced, so you have to add water. For alkaline, meaning hydrogen has been reduced, you have to also balance that up with hydrogen and oxygen with this heat. Then you have to multiply half equation by the hydrogen coefficient to balance the electron. So you add the two together and check the charge. Now, how do we really look about this? Is example here. Here we have Fe2Cl and Cl2 given Fe3 plus Cl. So first step, find the relation number. So now, the relation number here, remember when it's a ion, just carry the number from up and bring it down. Relation number here is plus 2. Chlorine here is diatomic and the thing is original normal statement of element, so it gives us 0. Fe3 plus, position number 3 plus. Cl minus ion is kind of minus 1. So we have 2 0 on the other side, there's 3 and minus 1. Now we bring out the half of the equation. So on the expression half, we have Fe2 plus Fe3 plus. And on the reduction half, we have Cl2 and Cl minus. But then taking it out, Cl2 will not just stand on its own, or 2Cl will not just stand on its own. So for that, sorry, Cl will not stand on its own. For that reason, we have to add 2 and the coefficient here with it. So that balances it out. So we have 2 atoms of fluorine and we have 2 atoms of fluorine here. So that balances that out. Now, over here, we have 32 plus, and then we now give, we're not adding the number of electrons to it. So adding 1 electron to this side because we have 2 plus here, and then we have plus 2 on the other side. So when you add 1 electron to this side, that will reduce this side plus 2 and make sure both sides are now equal. So for the chlorine, add to the left hand side. I have 2 electrons there. So adding 2 electrons there balances this out to this minus 2. Why is this so? Remember that chlorine here is neutral. So because it's neutral here, it is 0. Together we have minus two electrons there to make sure it is the same with the right hand side. Now, after we've done that, we move to the next step, multiplying by the inverse value or the coefficient that will balance it out. So we multiply the first line of the reaction with 2 and multiply the other line of the reaction with 1. So that gives us 2Fe2 plus 2 electron, 2Fe3 plus. And we are multiplying 1 or 2 doesn't change anything. So that is Cl2, Cl2, 2 electrons, and then 2 Cl minus. Now, why do we do this? It's so that we have the same number of electrons on the oxidizing side and the same number of electrons on the reducing side. Now, based on our law of mathematics, these two will now cancel each other. The 2 electrons here will cancel 2 electrons here. Now, when they cancel each other, it's not easy for us to write our equation straight up. Now, writing that out, we now bring the 2Fe3 plus 2Fe2 plus Cl2, which is on the second line. So let me point that out so you understand what we're talking about. This Cl2, we bring that, add it, then go to the first line on the right side, 2Fe3 plus, write that down, then this 2Cl minus, write it down. Now, by the time we now check, okay, what the charges on the left hand side, there's some on the right. Notice down there, for the Fe, that 2 times 2 plus, that will be 4. Now, Cl2 carries no charge, that's 0. So 4 plus 0 is 4. So on the other side, 2 times plus 3 is 8 plus 6. And then 2 times minus 1, which is the charge of Cl minus, is minus 2. So 6 plus minus 2 will give us what? Plus 4. So that means it will balance. So this is how you balance a complex reaction. Just so to look at the steps, let's go back to the video. So first things first, you check or assign the equation number. We have assigned the equation number as plus 2, 0, plus 3, and minus 1. 0 because it is neutral there. So yeah. Now bringing out the equation and vector have plus Fe2 plus and Fe3 plus, Cl minus, and Cl2 and then 2Cl minus. Now, remember, or looking at the original equation, the Cl there do not have 2. But because we are following the rule of balancing the number of atoms, we multiply the coefficient there with 2. That balances it out. Then coming down here, we balance the number of electrons. Electrons negatively charged. So we add it to the side that can be reduced so that both sides will become equal. So adding minus 1 to the product side for Fe, that balances that out. And adding minus 2 to the reactant side for chlorine, that balances that side out. Then we multiply by the inverse numbers to cancel out the number of electrons. So then we check charges. So that's it. Okay. And here I have iron 2 plus and okay, manganese. So that's reaction. So habitants. So Fe2 plus Fe2 plus so
Hello, sir.